You do not have to join an iClicker. We're not doing iClickers until we go back to being in person. So for today, we're just going to do polls inside Blackboard Collaborate. So hopefully you can all hear me, and then I'm going to go ahead and start our slideshow. Okay, so there's our slideshow. So I often start with a comic that's related to what we're doing today. This is more a general comic about physics and cats. As you know, I have cats, and I don't know if you knew this or not, but cats are the physicists of the animal kingdom. They are constantly doing physics experiments. Our cats like to knock things off of the mantle above the fireplace and such. They have lots of inertia. They like to sit around and do nothing for long periods of time. Anyway, so just to sort of start off our day, each day. I also like to start for a quick couple minutes with questions. Does anybody have any questions on anything general, not specific, that that you might be curious about?
Sir, I just had a question about the assignments that we did. They're called, I think, Bridge.
Uh-huh.
So if we have
Yes,
more
go
than
ahead.
so if we have more than 2 attempts, it's gonna decrease the percentage, right?
Yeah, it goes down by 10% for each guess.
Oh, I see. Okay.
Yeah. So it's not very much. Okay, any other questions? Okay, if not, just one thing I wanted to mention about tutorials. So our tutorials this semester are being coordinated by Dr. Simin Bagheri Najmi, sorry, don't always pronounce her name correctly, very bad of me. Anyway, some of you might know Dr. Simin Bagheri Najmi because she taught Physics 100, I believe, last semester. And I know a few of you took Physics 100. So because she's the tutorial coordinator, if you have questions about switching tutorial sections or general questions about how the tutorials are going to be run, she's the person to ask questions of that type of question. Okay, and then just a reminder that our tutorials will begin next week, and next week, so I think our first tutorials are on Tuesday, January 18th. And we'll be doing our first week in Zoom, and I will let you know once the tutorials have been set up in Zoom. Okay, you'll be able to see them in that Canvas Zoom, on that Canvas Zoom page. So any questions on tutorials? So Jason, somebody was asking if you lose points for getting bridge questions wrong, and the answer is yes. You lose 10% for each incorrect guess, which is it's going to be similar, I think, with the homework questions. It's going to be 5% for each guess that's wrong. Okay, so I wanted to do a really quick math poll mostly for my own information to get some idea, okay, of where you guys are in your math preparation and experience. So I'm going to quickly make up a poll here. And we'll do this one quickly. So just go ahead and add your answer once I get this set up. Okay, so there's our poll. So this is what our polls look like. And like I said, this is what we'll be doing instead of clicker questions for the first couple weeks. Okay, it looks like almost everybody, you just have to click on it. It looks like almost everybody has answered. So I will give you 5 more seconds. 5, 4, 3, 2, 1. And here are our responses. So you can see what everybody's answers are here. Okay, and so you can, so good, that's useful to me. So it looks like almost everybody, well, not almost everybody, about half of you are in Calc 2 right now. And then some of you, not a huge number, but some of you have finished both Calc 1 and 2. And then we have a reasonable number who have finished Calc 1. And so there are a reasonable number, though, who also are currently in Calc 1. So I will try to keep that in mind as we go along. We do use calculus in this class, but I try to explain it as I go. And it's not super advanced calculus, so most people usually handle it, even if they happen to be in Calc 1. All right, so I'm going to end our poll there. Great, thank you very much. That was helpful information for me. All right, so now we're going to move on to some physics. So what are today's concepts? Well, they're the concepts that were covered in the pre-lectures. It looks like most people were able to get into Achieve and watch the first pre-lecture and do the first bridge questions. So our topics are position, velocity, and acceleration, our sort of base kinematic quantities, which I'm hoping you're already familiar with, and then looking at one-dimensional kinematics, graphs, and constant acceleration motion. Okay, and today we'll spend a lot of time specifically looking at graphs and how we can learn about the motion from graphs, and how we can, for example, if we have a graph of velocity versus time, figure out what the position versus time graph would look like, and so forth. Because graphical analysis is a very important skill to have in physics. So you, as you saw in the bridge questions, one of the questions was asking you about the pre-lecture, and if you found that anything was still a bit confusing, or what your thoughts were on the pre-lecture. And so a lot of people said something similar to this first comment. We covered a lot of this in high school. I need a bit of time to refresh my memory, and that's completely understandable. This is the first part of this course is goes over topics that, like I said on Monday, you should have seen in Physics 11 and Physics 12, but we're going to go into them in more depth, and we're going to be using calculus to help us better understand these various quantities. And then a few other people also said it's been a long time since I've done physics. So, and I understand that, because you probably may not have done any in the fall, and then it may have been like Physics 12 might have been the beginning of your grade 12 year. So in that case, if you may feel like you want to do a bit of reviewing to get yourself back up to speed on the sort of fundamentals here. And then quite a few comments that saying, or at least some comments saying, I'm not familiar with integrals since I'm just starting to learn it in my math course. And my main comment on that is to not panic. Okay, that to not worry if you've not yet learned how to do integrals. That we'll only be calculating them essentially as the area under a curve on a graph. Okay, and we'll see that it's integrals are a way to figure out various quantities that essentially are calculated as a summation, but one of the quantities is varying over that summation. Okay, and you'll see as we go along that there are certain quantities that we treat this way, like work, for example, and rotational inertia. So, but as we go through, I won't ever have you do actual integrals. We'll just be calculating them as areas under curves. Okay, any questions on that before we go on? So we're going to do an example of this today. So let's start by looking at graphs. Okay. All right. So we're going to start. So this whole first pre-lecture and topic set here is on one-dimensional motion, 1D motion. And so here's an example of a position versus time graph, x versus t. Okay. And as you hopefully know, so this is a representation of an object's position as it travels through time. And if you wanted to, for example, figure out the average velocity of this object, that would be calculated as looking at the displacement, which is the change in position, delta x, which is the final position x2 minus the initial position x1, divided by the time elapsed, or the change in time, which is the final time t2 minus the initial time t1. Okay, and that's how you would calculate your average velocity. Okay, on average, how fast your object was moving between those two time points. Okay, and you can see, if you look at this, that this quantity, delta x over delta t, is just the slope of the line drawn through those 2 points, right? Because then delta x, right, is just your rise, right? Okay, and delta t would be your run, right? Delta x is the change on the vertical axis, and delta t is the change on the horizontal axis. And if you take delta x divided by delta t, that's your slope. Okay, so now something interesting happens if you start to reduce your time interval. So say you were to make time 2 closer to time 1, something like this, okay, then you can see that the slope changes a little bit. Okay, when you've got and that's because for this particular position versus time graph, right, the slope is changing, right, with time. It's not a constant slope curve, right? So as you change your time interval, your slope changes. And if you were to, for example, decrease the time interval to essentially 0, if you were to take the limit as your delta t approaches 0, then you get a quantity we call the instantaneous velocity, which is the velocity at that instant in time, and it's defined to be the derivative of position with time. Okay, so this quantity v, okay, is your instantaneous velocity. It's the time derivative of position with time, right? And this is essentially can be found to be the slope of the tangent line at that time t. So if you have a position with time curve and you want to figure out how fast an object is moving at any time, all you need to do is figure out what is the slope of the tangent line at that point. Okay? And that will tell you the instantaneous velocity. So let's see how well you guys can apply that. Okay, so we're going to apply this now, and we're going to, but before we do that, actually, let's talk a little bit about a derivative. Okay, so this is our sort of first introduction to differential calculus in here. So differentiation, I can't say differentiation, I can't say that word. Taking a derivative is basically a convenient method for calculating the constantly changing slope of a nonlinear curve. And most of the derivatives we're going to do in this class will be derivative polynomials, which is an easy one to do. And just to show you how this works, for those of you guys who are still in Calc 1 and may not have run into this yet, so here's what we call a polynomial function. Y equals a constant c times x to the n power, where c and n are both constants. If you wanted to take the derivative of this function, what we call the first derivative y with respect to x, it would look something like this. So you write it as dy dx. Okay, and then you plug in your function, c x to the n for y. Okay, and now when you take a derivative, since c is a constant, you can pull it out front, as I say, put it in front of that d dx, and then you apply the d dx just to x to the n. Okay, and it turns out when you do the derivative of x to the n, it's just equal to n times x to the n minus 1. So the exponent decreases by 1, and the former exponent n shows up in front of the number of the x, sorry. Okay, so for example, say your function is y equals 5x cubed, and you want to take your first derivative with respect to x. So the 5 stays there, and then you just take your derivative of x cubed, and that means you bring the 3 down in front, and your exponent becomes 3 minus 1, or 2. And so then your first derivative is just 15x squared. So, and that's pretty much, at least for the first part of this course, the only kind of derivative we will be doing is these polynomial derivatives. Okay, we'll get into a little bit later in the course, we'll be doing maybe some derivatives of trig functions like sines and cosines. Okay, but it won't get a lot more complicated than that for the most part. Okay, so now I have a question for you guys to try, another poll question. So I will set this one up, and then I will read it. Okay, so there's our poll. And so my question is, which of these instantaneous velocity versus time graphs, okay, goes with the position versus time graph on the left there? Okay, so you can see the blue curve there, all right, of x versus t. And the question is, which of the v versus t graphs is the correct velocity versus time for the same motion? And so someone was asking a question about the polls. I think you just click on the answer, okay? You don't actually have to, there's no submit button. So the poll questions for the first 2 weeks are not worth any points. So it doesn't matter, okay? They're not worth marks. The things will only start being worth marks when we do clicker questions, when we go back in person. Okay, it looks like almost everybody has answered the poll, so I'm going to give you 5 more seconds here. So 5, 4, 3, 2, 1. All right, everybody but 2 people have answered. Let's see what our responses look like. All right, so there is a lot of agreement on this one. Almost everybody, well, quite a few of you at least, think that the answer is C. So let's have a look at this one and see how you would figure out the answer. Okay, so remember, what did we just talk about? We said that the v versus t graph, okay, you get the v versus t graph from the slope of the x versus t graph, okay? Instantaneous velocity, right, is the first derivative of position with time, and that is the slope, right? So if we look at our position versus time graph, what do we see? We see that the slope begins with a constant positive value. Okay, it's essentially a straight line with a positive slope. And later, the slope decreases to 0. It curves over and decreases to 0. So then we go look at our velocity versus time graphs, and we say which one begins with a constant positive value and later decreases to 0. And there is only one graph that does that. Okay, there's only one graph that begins with a constant positive value. Okay, and so that right away is a dead giveaway. And then we have it decreasing to 0. So any questions on that? Good, all right. So so it looks like people have a pretty good idea of how that works. Okay. So now, shouldn't the velocity graph be smooth? In real life, it would be smooth. Yeah, in mathematically, it could not, there could be a discontinuity there. Okay, and in real life, though, it would be, yeah. Okay, but that's the closest. That's the only one that would constant. I mean, mathematically, this is a valid answer. Okay, so now let's go on and look at acceleration versus time graphs. Okay, so just like velocity can be found as the first derivative of position with time, acceleration, right, which tells you how fast velocity changes with time, is defined to be the first derivative, the time derivative, velocity with time. Okay, so in other words, acceleration is the slope of the velocity versus time graph. So for example, say you had a velocity versus time graph that looks like this graph up top, okay, this kind of funky, sometimes we call that a Mexican hat shape if you were to rotate it. But anyway, that funky shape for velocity leads to the acceleration versus time graph below. Okay, and if we take a look at it, we can see basically how these two correspond to each other. For example, if we look at the first part of that velocity versus time graph, we can see in the first part, the slope is negative. And so that means that the acceleration should be negative. And in fact, for that first part of the velocity versus time graph where the slope is negative, the acceleration is negative. And then similarly, where the slope is positive, okay, to the right of that velocity versus time graph, you can see if you go look at the acceleration graph, that for that part of the acceleration graph, the acceleration is positive. So that also makes sense. And you can look at one of the points in the velocity graph, right, where the slope is 0. Okay, where if you were to draw a tangent line, it would be horizontal. And you can see that corresponds to a point on the acceleration versus time graph where the acceleration is 0. And if you go look at the other 2 points there where the velocity is 0, sorry, where the slope of the velocity versus time graph is 0, okay, in the bottoms of those 2 dips also correspond to points where the acceleration is 0. All right, so you can see, and here's an example of a smooth velocity graph, right? Okay, you can see that direct relationship, right? You can see the fact that you can figure out the acceleration by looking at the slope of your velocity versus time graph. Great. Okay, so one of the bridge questions was on this. So just to point out that that's how you could have figured out this particular bridge question. If you go and look at that velocity graph, for example, you can see for the first part, the slopes were negative, right? And for the second part, you have positive slopes. It's a changing slope, but it's definitely positive to the right and negative to the left. And so the only acceleration graph here that makes sense, okay, is the one where the acceleration is negative, okay, on the left and positive on the right. So A would be the right answer here for this one. That was the only one that could possibly work. Okay, again, because of that relationship that the slope of the velocity versus time graph is equal to the acceleration. Great. Okay, so now what we're going to do is try and go the other way. Okay, so far we've seen, going back now to velocity versus time and position versus time, that you can figure out the velocity versus time graph by finding the slope of the position versus time graph. So here's a situation where the position versus time graph is a straight line, which means that it has a constant slope, right? And the constant slope there of that line is your velocity. Okay, and so the corresponding velocity versus time graph would be a horizontal line representing constant velocity. Okay, so the slope, again, of position versus time gives you velocity. Now you can also go the other way, and this is where our first introduction to integrals is going to come in. Okay, that you can start with a velocity versus time graph, okay, and find a position versus time graph by finding the area under the velocity versus time graph. Okay, and this is essentially doing an integral. Okay, but this is the way we are going to do them. So just to go through a couple of examples here. So say here's our nice constant velocity graph, again, our horizontal line for velocity versus time. And we're going to use it now to figure out what the position versus time graph looks like. Now we do actually have to make an assumption here. The velocity versus time graph cannot tell us what the initial position of the object is. So we have to make an assumption. If the problem doesn't tell you, sometimes the problem tells you, but if the problem doesn't tell you, then you have to assume something. And it's usually reasonable to assume it starts at x equals 0, at time equals 0. Okay, and so now what we're going to do is go through and figure out what's the area under the velocity versus time graph. Okay, and so the first area for the first second, okay, is just, it's a box, so it's length times width. Okay, so it's going to be 30 meters per second on the velocity axis and 1 second on the time axis, and that's going to give us 30 meters. Okay, and so that means that after 1 second, the position will be 30 meters if it started at 0. Okay. And you can see that that's, in fact, all you're doing here is calculating average velocity times time elapsed to get your position, which we know is the right way to do it, right? To figure out position if you happen to know average velocity. Okay, so now what if you do 2 seconds? Well, with 2 seconds, now you just calculate the area for 2 seconds, and that's our 60 meters. And so that means after 2 seconds, our position will be 60 meters. And after 3 seconds, it will be 90 meters. After 4 seconds, it will be 120. And after 5 seconds, it will be 150. Okay, and so you get what we expected, what we just saw previously, that for a constant velocity, a horizontal line there for velocity versus time, that you're going to get a linear x versus t graph, and that the slope of that graph, right, is just your 30. It's your constant velocity of 30 meters per second. So the slope of your position versus time graph is that constant velocity, which we know is supposed to be the case. Okay, so that's pretty straightforward, that one. Any questions so far? So remember, we started here at x equals 0, okay? If we started at some other x, then we would have to add the area under the curve to that other x to get the final position, okay? All right, so let's try this. So we'll do another poll here, and we've got 4 choices. Let me just start the poll first. There's the poll. Okay, and you can move it around in case it's in front of your picture. Okay, or I think you can hide it and make it come back again. Okay, but so here, okay, you're given a velocity versus time graph. Okay, and the question is which position versus time graph goes along with this velocity versus time graph. And now there's one extra fact they've given you, and that is that the initial position of the particle, the position at time equals 0, is minus 10 meters. Okay, so that's where the particle is going to start. Okay, and then the question is, what will its position versus time look like? How will its position change with time? So again, this is sort of you've got curves where you've got abrupt jumps, like the velocity jumps abruptly from positive 4 meters per second to negative 2 meters per second. And in real life, these curves, there would be a bit of a curve to that. You're never going to abruptly jump from a positive velocity to a negative velocity. So this is sort of a mathematical ideal, just to help you get the idea of how this works. I mean, the main difference in reality is that, like I said, you'll get curving off, okay? You'll get more of a curved transition between that positive velocity and that negative velocity. Okay, it looks like almost everybody has answered, so I think we'll do 5 more seconds here. So 5, 4, 3, 2, 1. Okay, so let's see. All right, so there is lots and lots of agreement here. A lot more, actually more agreement than the last one. Okay, so 132 people think that the answer is B. So let's have a look on how you would figure this one out. So like we just saw, to get position versus time, you want to look at the area under the velocity versus time graph. And what you see is that for the first part here, the area is positive. And for the second part, the area is negative. Okay, when you're below the x-axis or below the time axis, okay, below the horizontal axis, then that corresponds to a negative area. Okay, so that means to start off with, the position will be increasing, getting more positive with time, and then at time equals 5 seconds, it'll start becoming more negative. Okay, but it's already gone positive first, and then the other thing we have to realize is that x has to be minus 10 at time equals 0. So that basically that x equals minus 10 at time equals 0 rules out c right away, right? And so then it's either got to be A, B, or D, and then we look at it and we can see that the only answer that makes sense is B, right? Because that has a position that's increasing with time to begin with, up to 5 seconds, and then the position starts becoming decreasing, right, with time for the second 5 seconds. Okay, so well done. You guys seem to be quite good at graphical interpretation, which is good. Okay, that was a big part of the first pre-lecture here. Great. Okay, so now what we're going to do is have a look at the similar thing, just really quick, basically just to say that you can do the same thing with velocity and acceleration. So here's an example of constant acceleration with time, horizontal line, okay? And if you have constant acceleration with time, that is going to give you a velocity versus time graph that's linear, okay? With an equation that should look familiar, where the final velocity is equal to the initial velocity plus the slope of that curve, acceleration, times the time elapsed. Great. Okay, what if now back to position versus time, okay, and getting velocity, right? Getting position, sorry, from velocity versus time graph. But now what we're going to look at is a velocity that's changing. Okay, so rather than a horizontal line, we have a line with a positive slope, but we do exactly the same thing. Okay, we figure out the position by finding the area under the curve, but now the areas are going to be triangles. So now our area is 1/2 the base times the height. Okay, and the base here is our 1 second, and the height would be 10 meters per second. And so 1/2 of that, right, is our 5 meters. And so after 1 second, the object will have moved 5 meters. Okay, and again, this is the average velocity times time. Okay, And you can see that by, if you look at, because the velocity is increasing linearly, it starts at 0 and it ends at 10, then we know that for that time frame, that time period, the average velocity would be 5. Okay, and so this is just 5 meters per second times 1 second. That gives you your 5 meters. Okay, and then after 2 seconds, right, now you have the area of a triangle where the base is 2 seconds and you get 20 meters. And then after 3 seconds, you get 45 meters. Okay, and after 4 seconds, you get 80. And after 5 seconds, you get 125. And we can see that for constant acceleration, for a velocity increasing linearly, which is what constant acceleration is, that you end up with a position versus time graph. That's what we call a parabola. So you get position is equal to 1/2 the acceleration times your time elapsed squared. Okay, and so you can get that right from doing that area under the curve, essentially from doing that integral. And this is, like I said, at the very beginning of the class today, that's how we will be doing integrals in here. Okay, so and so you've got this. And the other thing to notice, okay, going back the other way, if you were given the position versus time graph and tried to figure out the velocity, looking at that position versus time graph, you can see that the slope starts at 0 and is increasing as time goes by. Okay, it's hard to eyeball that it's increasing linearly, but if someone were to tell you that's a parabola, then you would know that it was increasing linearly. Okay, and just to clarify, right, like I was saying, that when the velocity is positive, okay, that you're going to have a positive area. When the velocity is negative, you're going to have a negative area. Okay, and now this is where things get a bit more complicated. When your velocity varies with time, okay, with a curve that's not linear like this, if you have a general v versus t curve, okay, then to figure out your displacement of your object, right, the total displacement from time 1 to time 2, it would be the area under this curve for this interval, and this mathematically is what we call an integral. And so, and one way to figure this out would be by summing up the areas of the rectangles under the curve. And as you'll learn in Calculus 2, when you learn all about integrals and how they work, if you start to shrink those rectangles, the width of those rectangles down, in other words, if you take delta t and take the limit as delta t goes to 0, then this becomes what we call an integral. Okay, so the integral really is the actual area under that curve. Okay, and we, for the most part, will not be doing anything more than triangles in here. So, and here's mathematically what I just said in words, that the displacement, the change in position, would be the limit as you swing delta t goes to 0, and so it's represented as that integral. But don't worry too much about how this looks mathematically, okay? Though once you guys who do understand integrals, then great. Hopefully this helps you with a better understanding of what's going on here, but not to worry too much if you haven't gotten to this yet in class. Okay, all right. I mean, in some ways you can think of derivatives and integrals sort of being opposites of each other. Your math professors would probably yell at me for saying that, okay? Because as you can see, we know velocity is the first derivative of time of position, and going the opposite direction, position is the integral of velocity. So in a way, you can go back and forth between the two with either a derivative or an integral. But like I said, don't panic if you see integrals. All right, so in the pre-lecture, they did write them as integrals, okay? And so, and you can write a similar expression for the change in velocity. So the change in velocity can be written as the integral of acceleration over time between the two time limits, your time frame, okay? But the other thing is that we are mostly, not all completely always, but most of the time, we're going to be dealing with constant acceleration. Okay, so, and when acceleration is constant, doesn't depend on time. Okay, one thing you're going to learn when you do start doing integrals mathematically is that means you can pull that quantity out of the integral, and that makes our life a lot easier. And if you apply that here, you end up with some very familiar equations that hopefully you've run into before. You may have seen them written slightly differently, mostly in that at the university level in physics, we tend to not to like to use d to represent displacement. Okay, we like to talk about positions, okay, position on the x-axis, position on the y-axis, and we like to talk about change in position. Okay, so you can see in the second expression, we have the final position x is equal to the initial position x0 plus the initial velocity times time plus 1/2 the acceleration times time squared. Okay, and in the third expression, we have final velocity squared minus initial velocity squared is 2 times the acceleration times the displacement, x minus x0, which is your change in position. Okay, so I would like you to try to get used to writing all of your equations using x's and x0s and y's and y0s. We tend to start using y when we start looking at free fall motion and vertical motion. Okay, but these kinematic equations, as we call it, these three, as we're going to see when we start doing some problem solving, can be used to solve any one-dimensional kinematic problem with a constant acceleration. And so, so at this point, when you're solving a problem, you don't necessarily need to worry about which quantities of derivatives or integrals of which other quantities. Okay, that's most useful when you're doing your graphical analysis here. Okay, so, but just to look at how it relates to graphs. Okay, so constant acceleration, what does that mean? That means that the acceleration versus time graph would be horizontal, right? And then that would mean that the velocity versus time graph had a constant slope equal to that acceleration. Okay, and if the acceleration is positive, the slope will be positive. Somebody was asking in the comments about, well, what happens if acceleration is negative? Then it would basically, you'd have a horizontal line below the time axis, right? And your velocity versus time graph would have a negative slope here. Okay, as we're going to see next time, when we move to 2 dimensions, velocity and acceleration are actually what we call vector quantities, and that their magnitude and their direction matter. In 1 dimension, we tend to represent the direction as just positive or negative. So positive move means it's moving, say a positive velocity means an object's moving in the positive x direction, right? And negative velocity means it's moving in the negative x direction. Okay, and then what would the position versus time graph look like? Well, it would look something like this. Okay, because now, as we can see from our velocity versus time graph, also knows the velocity versus time graph at time equals 0. It starts at v0, our initial velocity. Okay, and then our position versus time would have a slope that is constantly increasing. Okay, and so we start with a smaller slope, and then it would get bigger and bigger and bigger as time increases, right? Because the slope, again, of the x versus t graph is the velocity. So that's what our constant acceleration motion looks like in graphs versus what it looks like with our kinematic equations. So any questions on that? Hopefully this is all coming back to you for everybody who hasn't done physics in a while. I usually start a little bit more slowly in this course because I know people are catching up. You would like to go over the second bridge question. I don't know if I'm going to have time today. We'll see if I have time today to do that. I might have time. Okay, and then just to show you the equations representing the 3 graphs. Okay, so x versus t is a parabola, and you can see the equation representing it is a polynomial that goes up to time squared, so second order polynomial. That the equation that represents velocity versus time is linear, and the graph is linear, and our constant acceleration again. Okay, so one of the most common scenarios where we use constant acceleration motion is looking at freefall motion. So looking at objects moving under the influence of gravity. Okay, and again, hopefully you remember this from when you did physics before. Okay, but on the surface of the Earth, objects experience essentially constant acceleration due to gravity that points towards the center of the Earth. Okay, so if you were to take an object and throw it upwards with special upwards velocity, okay, then that constant downwards acceleration would cause, in this case, we're using the x axis to be our vertical axis, would cause Vx to start positive and become smaller as the object rises. Okay, it will reach some maximum point where the velocity will go to 0, and then it will start to gain velocity in the negative direction. Okay, and so it will reach a maximum point where its vertical velocity is 0, and then it will be speeding up going down. It becomes more and more negative as it falls down. Okay, this is a nice example of constant accelerated motion. Okay, and if we look at our velocity versus time graph, it would look something like this. Okay, so here is a constant acceleration in the negative direction. So our velocity versus time graph would have a constant negative slope. Okay, and so you can see the velocity starts with a positive value, gets smaller as the object rises. That point where the dotted line is drawn, that's your maximum point where the velocity goes to 0. And then when you get past that point, then the velocity becomes more negative as you go. And if you look at the corresponding, and this is our acceleration due to gravity. Okay, so the slope of that graph there, right, would be your, hopefully you're familiar with your acceleration due to gravity, your minus 9.8 meters per second squared, or 9.81. Most of the time we'll be using minus 9.81 because most of our questions, they'll give you 3 significant figures for most of the quantities. Okay, and then that corresponds to a position versus time graph, which looks a lot like what we expect, where it rises to some maximum height and then it falls again. Okay, so we're going to be, next time, we will combine this one-dimensional vertical motion under the influence of gravity with horizontal motion, okay, and look at what's known as projectile motion, which is what happens when you throw an object right on the surface of the Earth, and it has both, it is experiencing both that constant acceleration due to gravity, but typically, unless there's air resistance, no acceleration in the x direction. Okay, so so we've run out of time, so I'm going to stop there. I know some people wanted me to explain this one, the checkpoint, and I was going to if I had time, but I don't. So I can start next time with a quick explanation of this one if people would like. Okay. So I will do that. I'm going to stop the recording now.